Okay, so this is a question from the homework. This was page 563, number 57. And for these, you're supposed to use the inverse trigonometric functions to find solutions that are in the given interval. And then approximate to 4 decimal places or whatever. So 15 cosine to the 4th x minus 14 cosine squared x, and then plus 3.
Yeah, this one was.
Equals 0, and now this is on 0 to pi. Okay, so we're finding all solutions to this. So I'm imagining it does something like this, whatever it does, and there's some interval, maybe here's pi, here's 0. We're supposed to find these zeros, right? However many we find in that interval, that's what we're supposed to do. So, okay. First thing I'm going to do is make a substitution, because I notice this has quadratic form, right? This is an equation that has something here, there's a term here, and then if you square that term, it shows up right here. And so what I'm going to do is I'm going to take whatever this term is here, I'm going to let it be a. Let a equal cosine squared x. So then if I square that, and remember this is just cosine x quantity squared. If I take that and square that, right, in other words a squared gives me that thing right there, right? That's the same thing as cosine to the 4th x. Okay, so I'm not telling anybody anything new, right? Hopefully everybody should have got to this point, so then they can make this substitution and go 15a squared minus 14a plus 3 equals 0, and I notice, I could solve for a because I'll just use a quadratic formula and say a equals negative b, so that's going to be negative is positive 14, plus the square root of that squared. I'm going to go ahead and do that. Let's go ahead and square out negative 14. I know it's going to be positive, so I'm not going to bother with the sign. This is 16, that's a 4 and a 5. Stop me if I'm doing this wrong. 196.
Yeah,
196 minus 4 times a times c, all over 2 times a. Okay, so let's clean this up a little bit here. 4 times 15 times 3. 4 times 15 should be easy. 60, yeah, there you go. Right? Yeah, 30 and then 60, yeah. Then you multiply that by 3 and you get 180. Yeah, nice. So in here, since we're just knocking this out, I'm going to go ahead and do this. That should be 180 right there. 180. This 2 times 15 should be 30, I think. Now, 196 minus 180 should be 16. Is that right?
Yeah.
That's right. Okay. So that is this. That works out to this right here. What's the square root of 16? 4. Oh man, this is getting really easy now. So get rid of that square root. We're just going to replace it with a 4. So now we have two possibilities. A is either equal to 14 plus 4 over 30, or A is equal to 14 minus 4 over 30. Everybody with me so far? Is any of this brand new or crazy or anything? I don't think so. A is 18 over 30. Did I do that right? 14 plus 4 is 18, right? Half of that would be 9 over 15, which is what?
3/5. Yeah.
3/5. Okay. 14 minus 4 is 10 over 30. When that one's easy. That's 1/3. Everybody got that?
Yeah.
Okay, so we have two possibilities for cosine squared x. And so I'm going to get rid of all this stuff over here. We know how we got that. That's fine. But now we have two possibilities. A is either equal to 3/5 or A is equal to 1/3. But A, we said, is cosine squared. Okay, so cosine squared is equal to 3/5, or cosine squared is equal to 1/3. So now,
Square root of both sides.
we're going to square root both sides. When we do that, we're going to get positive and negative answers, right? Taking a square root gives us two possibilities. And notice, this is the degree of this polynomial. If we can think about it as a polynomial if you get rid of the cosine, just say that's a, or something to the fourth, something squared. We should expect 4 roots. Or maybe not. Maybe not. But here's what we're going to do, right? Because if this were 15x to the fourth minus 14x squared plus 3 equals 0, we'd say, well then, there's 4 roots to this. We know that from the fundamental theorem of algebra, right? It might be the case that some of them are complex. We might end up with imaginary numbers popping up. But we could say that absolutely, without a doubt, there are exactly 4 roots to this guy.
And can some of them be like...
Some might be repeated.
Yeah.
Right? Yeah, that is possible. But here we go. So I'm going to take the square root of both sides. When I do that, I'm going to actually do this in 2 separate ways. I'm going to go, okay, on one hand we have cosine x is equal to root, I'm just going to do it like this, root 3/5, or it could be the negative of that. So we get cosine x is equal to negative root 3/5. From this one we get 2 possible answers. Cosine x is equal to the positive 1 over root 3. Or cosine x is equal to the negative 1 over root 3. Now, okay, let's think about this. It looks like in both of these cases, let's see how I want to do this. Okay, first off, I want to think about what's going to get pulled back where. One way of doing that is to do this and say, okay, here's pi,
Well,
here's pi over 2, here's 3 pi over 2. Now, I also want to make sure I got the magnitude right here. So, root 3 is bigger than 1, yeah?
yeah.
Right? 1 is less than the square root of 3 because 1 is less than 3. Right? Take square root of both sides and you end up with that. So therefore, if I divide both sides here, I end up with this. Oh, and by the way, this is also
Well, the
true.
bigger one, if it's bigger on the bottom, it's always less than 1.
There you go. Right? But I'm just want to be explicit here. So this is some number between 0 and 1, so it has, so then there is some number in cosine that's going to pull that back. And I'm going to go ahead and say, here's 1 over root 3, it lives right there. And this is where that guy should pull back to. The other one, negative 1 over root 3, lives somewhere down here. And when I take our cosine of him, he's going to show up right here. So we have these points. Now the other one, root 3/5.
Well, 5 is bigger than 3.
5 is bigger than 3, so we know that that's between 0 and 1. I want to do one more thing though. Just because I already have this written out there, I want to find out, is root 3/5 bigger than or smaller than 1 over 3? So how is this thing related? 1 over root 3. I don't know. I'm just gonna, this is my shorthand for, I don't know if it's less than, bigger than, whatever. I'm just gonna do this. I want to multiply both sides by the denominator, noting that everybody's positive. And I get root 3 times root 3 over here, root 5 over here. 9 is somehow related, 3 is somehow related to root 5. I think that's bigger than that. I think 3 is bigger than root 5. Because 9 is bigger than 5.
Yeah.
So root 9 is bigger than root 5. And that's the same thing as 3 being bigger than root 5. So now we can bring it all the way back and say that's true, therefore that's true, therefore that's bigger, therefore that's bigger, therefore that's bigger, therefore that's bigger. So he's a bit higher up. We don't need to know that to actually solve this. I just wanted to know. So root 3 over 5 gives me a guy right here. Another one, negative root 3 over 5, would then pull back to right here. So those would be each of them. And one thing I could see with this, notice it said, oh, I got rid of it. We're on the interval, 0 up to pi. Every one of these lives between 0 and pi. Does it not? Right? When I pull each one of these guys back. Now, another way of thinking about what I've just done conceptually here is to think about the graph of arc cos. Arc cos starts here, comes up like that. Up here at pi, here at pi over 2, up to 1, down to -1. And notice that each one of those things, that's what I'm about to plug in, right? If I take arc cos of both sides, I end up with x is equal to arc cos of root 3/5. And so now what I'm doing is I'm saying, well, if I plug in root 3/5, we know he lives somewhere over here, root 3/5. And as far as arc cos is concerned, he will return you a value that is indeed between 0 and pi, right? Because here's 0, here's pi. So whatever arc cos of root 3/5 is, you're good to go. Ditto with this guy. 1 over root 3. You plug him into arc cos, and out pops something still in the first quadrant, which is, by the way, look at this. Like this picture is the same thing as this picture, it's just been flipped, right? Two different ways of thinking about the exact same thing. And so I plug in whatever happens to be in the calculator, or whatever I'm using, plug in root 3, or 1 over root 3 into arc cosine, and what pops out, arc cos 1 over root 3, will be between here and here, which is exactly one of my bits, right? And so I need each one of these. I need the -1 over root 3. I'll plug him in, and my calculator will give me a number that's between pi over 2 and pi, and that's arc cos -1 over root 3. Finally, I plug in -root 3/5, and I get one last number, arc cos -root 3/5, and that's what each of these points are right here. The -1 comes out to be this one, which we just said was arc cos -root 3/5. This one is arc cos -1 over root 3. This one is arc cos 1 over root 3. This last one is arc cos positive root 3/5. And those should be your four answers. That one, that one, that one, and that one. Conversely, that one, that one, that one, and that one. So you got an imaginary number?
Yeah, I think the problem was somehow I ended up with -3 over 5 and -1/3. So then when I plugged it in, it took the root of the cosine.
Yeah, that's an honest mistake. That happens. That happens. And if that happened, what could we infer from that? Let's say that Victor did it right, and that it came out to actually be this. And then you got this. And so then you went to take the square root, and you ended up with, in every case, you'd have an I times each one of these. I. What would you conclude from that?
There's no solution.
There's no solution. In the same way that if you have a polynomial, say x squared plus 1 equals 0, and you're going to find the roots, well, what does that thing look like? Well, this thing would look like this. And you're saying, well, and you're asking, where does it cross the x-axis? It doesn't, right? This thing does not cross the x-axis, right? X plus 1 does not cross the x-axis. And so if you ended up with these i's, that would tell you that this, if you consider this thing as a function, and if you were to graph it, it would be entirely above or entirely below the x-axis, and it wouldn't intersect anywhere. It's another way of thinking about it.
Could you graph cosine on an imaginary plane?
The cosine, you can put imaginary numbers into cosine. You absolutely can. And that's what you do later on. For right now, we're worried about only real inputs and real outputs. But if you put in an imaginary input, well, there are imaginary inputs you could plug into cosine that will give you imaginary outputs. And so it is possible to solve this thing. Say cosine squared x equals negative, say negative 1. You say you take the square root of both sides and you get that cosine x is equal to plus or minus I. And that does have a solution. It's just that, that this number now is a complex number. In other words, this x would equal a plus ib for some real number a and some real number b. Interesting stuff. Any other questions? Did I answer your question?
Yeah.
So yeah, just a sign popped up somewhere that it shouldn't have. Nah. Not worried about that. Okay. Are we ready? So, one thing I want to say, for these right here from 495 through 496, it is a chapter review. And so, you'll notice you have 64 and 68. The even numbers are in the back of the book. Chapter reviews have answers to every single one of them. Okay? So, I expect that you're checking your answers in the back of the book, and those are in the back of the book. Now, on 68, it will be much to your benefit to use an approximate value. I believe it's decimals, so make sure you can do that. Okay? Keep your answer to 4 decimal places. And all the other stuff is going to come up as we talk. Okay, so here we go. Oh, and you'll notice this stuff, we're picking up stuff that we had to skip from last homeworks, from previous homeworks. Okay, these 2 questions we couldn't have done from homework, whatever it was, 11 or 10 or whatever it was. This stuff, these were problems that we could not do from our previous homework 11. So yeah, the other one was 10, I think. So yeah, we're, like I said, after we learn what the inverse trig functions are, we're going to go back and see how to apply them. Now that I've said that, that should be a big clue as to what you need to do to solve this problem. Okay, so we have alpha, beta. This is gamma, and gamma is understood to be 90 degrees. And you're given that the side A is equal to 31, side B is equal to 9, and you are to solve the triangle. And all that means is find all the unknowns, right? For every triangle, we have 3 angles, 3 sides. Okay? You should have known that for years now, right? Every triangle has 3 angles, 3 sides. To solve it means to find all of them, given some initial bits. You're given that that's 90, and you're given that.
So, Pythagorean theorem.
C
Okay, let's do that. C is equal to what?
root 31 squared plus 9 squared.
There you go. 31 squared plus 9 squared. 9 squared. There we go. Which we can figure. That's fine. We're done. I'm done with him. As far as I'm concerned, I'm done.
Sine of alpha equals 31 over that big thing.
I'm not even going to write it. We know what it is. So now what? Did it tell us to find sine of alpha? Take arc sine of both sides, right? So alpha is equal to arc sine of this stuff. 31 over 2. Now, but this is where I want to stop us. That's perfectly good. That is a perfectly good answer. And if you were to plug that into a calculator, you would get a decimal approximation that you'll find in the back of the book. In practice, if you are given, you could think about this as exact, that these are exact values, okay? Now, we did some magic and derived a new value, okay? So in practice, it's good to try to get as much stuff as you can out of here. So like right now, we're trying to get alpha. We don't want to use something that has been derived. I mean, you can, like I said, it'll be just fine. But if you have the option to use the given values, it's better to use the given values. How could we relate alpha to these two given values?
Tangent.
Tangent. And another thing that's nice about that, it's not always going to work out this way. But anytime you have, because, okay, we'll just do it this way. That's that over that. Now what do I need to do?
Arctangent.
So that what equals what?
The alpha equals arctangent of 31.
Arctan of 31 over 9. Now here's the nice thing about this. Do you ever have to worry about what you're plugging into arctan? It works for every single real number, no matter what. Do you have to worry about what you're plugging into arcsine?
Yeah.
Yeah, and so it's another little thing that might trip you up, especially if you happen to have done this wrong, and you end up maybe putting 3 squared plus 9 squared, and then you go to do this. What would 3 squared plus 9 squared be? That would be 9 plus 81, and that would be the square root of 9 plus 81, which is the square root of 90, which may not be, I don't know if that's bigger than 31.
Yeah, I don't think it.
It's not. The root 90 is certainly less than 31. So then when you take this, you'll end up with this. So if you happen to mess that up, okay, you get a sixth of the problem wrong. Yeah, big deal. But now you go to plug this, you take your wrong thing. This is why it's not good to use derived stuff. If you can, use the given stuff. If you derived the wrong number and you tried to plug it into here, uh-oh, your calculator's going to go, no, and it might catch on fire, and you're like, what just happened? I don't know where I went wrong. It's because you messed this up, right? So, but hopefully you're not going to mess anything up. What are the odds that you'd mess up a calculation, right, Victor? Right, so this is what I'm saying. Like, this is one of the ways you could hedge your bets, right? If you have the option to use arctan, use arctan. If you don't have the option to use arctan, well then you can't. But what you should do is use the given values anytime you can. But now that we know that that's what alpha is, and I think in this part of the homework, which should be these guys, 13 and 15, I think it wants you to do the answers in degrees. And so you're going to then plug this into a calculator in degree mode, or you could get on Wolfram Alpha and write arctan, parentheses, 31 divide 9 deg, and it'll do it for you. It'll give you an answer in degrees. Or, does it work? I think it handles it this way. You might have to go on the outside deg. Because otherwise, if you just do this, it'll certainly give you the radians. So on Wolfram Alpha, you could certainly do this, 31 divide 9, 2 deg, and it'll say, it'll give you that in radians, and then it'll convert it to degrees for you. Whatever, who cares? The point is this, what's beta?
Tan again.
You could, okay, so you could use arctan of this over that, because tan beta is equal to 9 over 31. That's a perfectly good way of doing it. And then you say beta is arctan 9/31. And you're absolutely good. Or you could say, like if I told you that that was 30, you would tell me without hesitating, that's 60. If I told you that's 25, you would tell me, well, that's whatever 90 minus that is.
So it would
So
be
it's alpha.
90 minus arctan of 31/90.
There you go. 90 minus alpha is equal to beta. And so, 90 degrees minus arctan 31/9 is beta. There you go. Now, if we were in radians, what would you put right here? Pi over 2. There you go. There you go. Okay? So you're going to go back and do a couple of those. All right? Now, another way, yet, we could get C. There's another. How can we get C without using the Pythagorean theorem?
Sine of alpha.
Sure. There you go. Sine of alpha equals what over what?
31 over c.
31 over C. So the C is the thing we're looking for. Let's get him upstairs. bring that downstairs.
Sine of alpha.
But alpha we know is, oops, that guy. So we could say then C is equal to 31 over
Which is
sine of arc tan. Yeah. This is what I'm saying. Like, we did not want to go down that route. Like, if you did, then that whatever. But I'm just saying, like, this is on the board, but we didn't actually want to take this route. But that's on the board, and so that's what I'm going to use, 31 over 9. And that would be a perfectly good answer. I think for these, they want you to approximate using decimals. If I asked you for an exact answer, this is what I'd be looking for. Either this or this is what I'd be looking for beta. This is what I'd be looking for alpha. And if you chose to go this route, that's cool too. It's just beware, because your final calculation is dependent on a previous calculation, whereas this is dependent on given information. And so it's one step removed from a possible error. Everybody get what I'm saying with that? Okay. So there's nothing wrong with doing it any of those ways. We could have used arc cos. There's a bunch of different ways we could have done this. It's just that you're minimizing your chances of a mistake if you use the given information. So, I forgot to set a timer. Let me set a timer for today real quick. Oh, come on, you. Okay. All right. Now, okay, here's the hard stuff. Now, get ready. So we have number 36, so to correspond with this. So from the problem set on 468 through 90, number 36, there's like A, B, C, D, and E. Problem A gives you this, sine theta is equal to 0.8225. And it tells you to approximate theta to the nearest 0.1 degrees for all angles. For all angles theta in the interval 0 degrees to 360 degrees. Not including the 360.
So 0 to pi.
So in other words, 0 to 2 pi. Okay? I wanted to actually do a degree example here, and we'll do a radian in a second. So for this one, what I suggest you do, you can do this a bunch of different ways. What I like to do here is just say, well, hold up, wait a second. That's just sine theta. I know what sine theta looks like, and I know what sine theta looks like on the interval they gave me. Now, if they gave me a different interval, I would draw it differently. But since they gave it from 0 to 360, I'm just going to go ahead and draw sine on 0 to 360.
Why can't you include the 360?
Because, well, I don't know why. There's a couple different ways, reasons why you might not want to. If you include the 360, then you've wrapped back around. That's usually why you don't see it included. But it doesn't really matter. They could have asked for it included. It doesn't really matter here. Now, since we're working in degrees, how many degrees is that? 180. And this guy occurs where?
90.
90. Okay, 90.
Wait, so if you graph sine on Desmos and turn it to degrees, it would look way different.
It would. It would. But here we're understanding that you're converting, right? Like you take 90, convert that into pi over 2, and then plug it into sine. So there's kind of some magic going on in here, but we're not going to worry about that too much. So here's the thing. This is 1, and so 0.8225 lives somewhere around here. 8225. And so I know what to expect now. I know I should expect one answer to be here between 0 and 90, and another answer to be between here, between 90 and 180. Now here's the really cool thing. Because this thing is symmetric, this distance, whatever distance this happens to be, I'm going to call it D, is exactly the same as this distance right here, D.
Yeah.
This is how I think about it. In your book, it has some ways of finding all of these. There's a nifty little formula, and it's a real pain, and I hate it. If you just look at it, and remember that even though you haven't drawn it perfectly, that distance is the same as that. If you know what number that is right there, then how would you find that number right here? Given that that's 180, you take whatever D is and subtract it. Take 180 and subtract off D, and you'd end up right there.
Yeah.
Now here's another thing though. We know that the outputs of arc sine will give you things from here back to here, right? So if I just take arc sine of this thing, right, theta equals arc sine of 0.8225, it ain't going to give me this one, right? It's going to give me this one right here. I'm going to call him theta 1. This right here is theta 1. That's how I like to do it, right? If you're more comfortable doing it with the picture of arc sine, and you say, okay, well, if here's 1, here's 0.8225. When I plug him in, I'm going to get this answer, theta 1, and he's going to be between, I guess 90 degrees. It'd be between 0 and 90 degrees. That's my theta sub 1 right there, right? Couple different ways of doing it. I like just doing it right here, knowing that if you have some output, you don't know where it came from. It could have come anywhere from over here, maybe at 700 billion. I plugged him into sine, and out popped this right here. If I plug that into arc sine, he's going to pull back that angle right there. That's theta 1 that he's going to pull back. I also know that that's a positive value. So then I'm going to to find the other one, which is what I'm going to call theta 2, I'm going to take 180 degrees and subtract off whatever theta 1 was. In other words, 180 minus arc sine of 0.8225. If you're doing this, you want to make sure you're in degree mode, otherwise you're going to get junk. Okay? If you're working in degrees, make sure your calculator says deg somewhere on it. Okay? So there's that one. Any questions on this? So there are two answers here. One was this guy. The other one was this guy. And there's no more between 0 and 360. That's another nice thing about having drawn this out, is I could just look and see, is that the entire interval? Yeah. Did I get all of them that intersect this line right here? Yeah. So I'm done. That's one answer. That's the other answer. You want to check in the back of the book to make sure that when you plug that into the calculator, you get some, however many digits. Check it in the back of the book. Ditto right here. All right. Moving on. Can I move on? Yeah. All right. Still 36. I think this is E. This one's a little bit more involved. This one is E, and it's secant theta is equal to 1.4291. We want to approximate theta to the nearest, blah, 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 for all of those in that interval. Since it's that interval, I'm going to sketch secant on that interval. Secant is what you would get if you took cosine, but then did 1 over that. And so we have an asymptote here. We have an asymptote here. Let's get all of these. That's 360. This is 180. That's 90. This is what, 270?
Yeah.
Okay, now secant is what I get when I divide by the dotted line, basically. And so, okay. Now, how high up is this right here? 1. And so 1.4 must live up here somewhere. 1.4291. And so I expect then, how many answers should I expect? 2. We have one here, there's theta 1.
One
The
positive.
only other one is going to be right here.
Oh, okay.
We're going to call that theta 2. So I'm searching for theta 1 and theta 2. Here's the thing. You don't have an arc secant key, right? You have an arc cosine key. So what I would do, I have this picture in my mind, or I've drawn it out because I'm a good student, and I draw out what's going on in my head. And but since we don't have an arc secant key, we're going to have to use something else. What can I do to this? What do you think you might want to do? What is secant?
One over
cosine.
So I could
Five.
I could rewrite this thing
Flip
as
both
1
sides.
over cosine theta is equal to 1.4291. Now, can I get that cosine theta by himself?
Yeah. So multiply both sides by cosine and divide this side. 1.42.
There you go. 1.4291. Now, how do I get that theta out of there?
Arc cosine.
But now, which value is that going to give me? Because it doesn't give me 2 values, it's only going to give me 1. If you think about it, right, here's arc cosine, it does this thing. Here's 1, here's -1. I'm plugging in a number. Is this number positive or negative?
Positive.
So it's somewhere over here. And so it's going to give me some value that's, in this case, I guess we go up to 180, and here's 90.
Wait. Oh,
Right? Another way we could think about this, and the way I prefer to do it, is to say, well, hold up now. Wait a second, what did we just do? We just had this, and we've just turned it into this question. And the thing is, like, okay, 1.4, whatever, 1 over 1.4291 does something like this. The thing to notice is that these are the same places, right here and right there, where I didn't do that very well. But you see what I mean, right? This is the same place right here. This is that right there, right? Like that's what it means. If you take 1.42, like that's secant. It's the same places it would be, right?
yeah.
Like all of, I'm not saying that very well, but what I'm getting at is this is the same theta 1 right here.
Yeah.
This is the same theta 2 right here. Now, when I plug this into arc cosine, is this going to give me theta 2 or theta 1?
Theta 1.
Theta 1, because it pulls back only things in the first 2 quadrant, right? Or the first 2 quadrants, from 0 up to pi, or from 0 up to 180 in this case. And so, whatever this happens to be, when my calculator is going to give me that value right there. It's going to say that's theta 1. And it'll be between 0 and 90 in this case, because there's 90 degrees. And you should check that. When you plug that into your calculator, after having reasoned this out, you should anticipate beforehand, before you actually see what that is, you should have a good grasp of this to say, when I hit enter, after I've typed inverse cosine 1 divided by 1.4291 into parentheses, before I hit enter, I'm looking for some number between 1 and 90, or 0 and 90, okay? And when you do that, and it pops out a number between 0 and 90, you can feel confident that you did the right thing, okay? How do we find theta 2?
The same. It's like 360 minus.
Yeah. Yes. Because in this case, right, with this kind of symmetry, this is symmetric over this way, right? And so this distance from here to here, let's call it d, is the same as this distance. And here's 360, right? That's the full period right there. This is the same as that. And so then that value right there occurs, theta 2 happens at 360 degrees minus that bit right there. That bit happens to be the same as that number, right? So minus theta 1, or in this case, arc cos 1 over 1.4291. Did we find all of the values from 0 to 360?
Yeah.
Yeah, we did. One of the things is like, if you had that, it would, like, if you did include that, it might be a repeat value, in a sense. You know what I mean? Like, because it repeats. So like, if you happen to have an answer, like, if it were instead of this, it's equal to 1, well, you'd have it here, but you'd also have it here, but that's exactly where it repeats, right?
Yeah.
So that's one of the reasons they leave that out, because if you know it without that, then all you have to do is just take each of your answers and then just add 2 pi to them for however many times you do. But if you include that and you found that, now you're adding 2 pi to all your answers and you're picking up an extra one every single time.
Yeah.
You know, so it's just, you know, that's my guess as to why they decided to chop it off. They could have kept it in. I might keep it in on a quiz, who knows. Okay, so did everybody get all that?
Yeah.
So like I said, your book has some nifty little things about how to find all of these. I prefer, you can look at the book and see what the book says, and if that makes more sense to you, great. I prefer to do it graphically and just say, well, that little bit's the same as that little bit. And we'll do that right now with this one. So this is the same thing, but now it's to the nearest 0.01 radians, and theta is on the interval 0 up to 2 pi, not including 2 pi. This is number 38. And we're just going to do one of these. This is 38A. A is negative 0. Oh, I'll do it the other way. That's right, I wrote it backwards.
Negative.
When I wrote it down. Sine theta is equal to negative 0.0135. So again, same thing. I want to get an idea of what's going on. So I'm going to graph sine theta on the given interval. That way I'll know what to anticipate. Sine starts here, comes up, goes down, comes back up. There's pi, there's 2 pi. We have a negative value now. And I notice that that negative value is indeed between 0 and negative 1, so we're good to go. And so now, did that pretty well, okay. So I'm just going to draw it, it doesn't matter where, I'm giving myself room. It should be way up here, but whatever. Negative 0.0135. Okay. So how many answers should I expect? 2. Because we only care about solutions from here to here. How many solutions are there to this equation?
Infinite.
There are infinitely many, right? It goes both directions. You can find infinitely many. But on this interval, there's only 2. And so I'm going to name them. I'm going to call this one theta 1. This one theta 2. Now, so this point right here, what's the radian value for where that point occurs? So that's pi, that's 2 pi, that's 3 pi over 2. So, in other words, theta 1 is in which quadrant? Third quadrant. Theta 2 is in which quadrant? Okay, we could use that to help check our answer at the end. Here. Now watch this. We go to solve this bad boy, and we get theta is equal to arc sine negative 0.0135. Which one of those is it going to give me?
The one in, wait, yeah, the one in the third quadrant. Oh.
This is where it gets really tricky. Because it's neither of these. Notice how I didn't put theta 1 or theta 2 right here. Because what does arc sine do? He only knows about these values between here and here. And so if you say, hey, arc sine, where did this come from? He's going to say, well, you must have come from right here. That's where you came from.
So arc sine is wrong.
Yeah, arc sine is wrong, right? You have to use your brain. It's just like, oh, I took the square root of 4, it's 2. Well, But your original problem, it should have been the negative one, right? It's just like that, right? Like, but check this out. Look at this distance. This distance is the exact same thing as that distance right there. But here's the problem. You don't want to take 2 pi and subtract off whatever this says. Because is that a positive or a negative number?
Want to add it?
Yeah. Yeah. So there's a couple different ways we could deal with this, right? I'm going to start by getting theta 2. Theta 2 is, and what I'm going to do right here, I'm going to say, all right, here's d, here's the distance, d. This is the same distance, d. This is the same distance, d, right? Well, I don't think we ever really proved this, but it should be clear that the way we derived this graph from a circle, that all of these things are symmetric. This is symmetric over here, this is symmetric over here, this is symmetric right here. I mean, there's nothing more symmetric than a circle, and you get symmetric things when you project from them. But anyway, so whatever that distance is, theta 2 is where you would end up if you ran all the way to 2 pi and then went back by d. So you go from 2 pi and minus off d. That's what theta 2 is. Problem is, if you simply say, okay, well, that's d right there, you have to consider, is it positive or negative?
So minus the absolute value?
That's the way I think about it. I could just say it's always going to be minus the absolute value of something. Then you don't have to worry about whether it popped up over here or over here. Okay? Now maybe we should have done this one first so that because we didn't have to address this in our first problem. Right? We just said, oh, you just subtract off arcsine. But my point here is don't get complacent with this. Right? Don't just say, oh yes, I take either pi or 2 pi and minus off arcsine and I'm good. Not necessarily. But if you think about it as the absolute value, then that distance is the absolute value here. Arcsine of negative 0.0135. And there you go. Indeed, that's theta 2. Okay? Now, you could, if you were so inclined, say, well, it's also the same thing. Theta 2 is 2 pi. Since that's a negative number, I could just go plus arcsine.
But when you plug in a negative to arcsine, doesn't always give you a positive. Oh, no, that's arc cosine. No.
Right? Arc cosine will always give you a positive number. Arc sine might give you a negative, it might give you a positive, and so you could think of, well, since it's negative, I could minus it off, and a minus minus is a positive, and yeah, you'd be right, but I think it's much easier to just say, well, hold up, let's just think about distances here. This is the distance that it gave you from here to here. And if I took that same distance and did it from there to there, but distances are always positive, so always just take the positive, and you should be good. So then, how do we find theta 1? Theta 1, where do I start, and then where do I run?
Pi
Start at pi.
plus absolute value.
Plus the absolute value of arc sine, negative 0.0135. Now there are certain tricks, like I said, your book has some tricks for like, and see, the thing is, like there's a way to do it so that it always works, like you plugging it into the same formula every single time. Problem is there's different ones for arc sine and arc cosine, and you'll never remember those. You'll always, wait, was this the one with the 2 pi or is this the one with the pi? Was this the one with the absolute value? Or you can just look at the picture, right? Just look at the picture and use the picture. That's why I'm not even going to bring up, I'm not even going to put on the board what the book says about the little nifty tricks and stuff like that, because I'd much rather do that. Okay? So you're going to get a lot of practice with this stuff. This stuff is super important. Being able to do this right here, this type of reasoning. I've suggested that you do it visually. Okay? That's the way I always suggest. All the years that I've been teaching and tutoring this, this is what I suggest to do. There are shortcuts in your book, but I'm telling you, with those shortcuts, there's a payoff, or, there's a trade-off. Like, you will have to memorize more stuff, and it's super easy to get those things confused with other stuff, and I just think this is much more straightforward. But if you want, you can look at the book, check that out. Okay, can I get rid of this? Okay, so it was this guy and this guy. Those were my answers. For these, it does say approximate to the nearest whatever, so you will need to do that in a calculator in your final answer. But I would say that you get all the way to where we did before you go and plug that stuff into the calculator. Get all the way to the end, then plug the value into the calculator. It's much more trustworthy than trying to carry around a bunch of decimal points and blah, 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 blah. Okay, now. These, 37, 43, this one, and this one. These are all applications problems.
Like word problem.
Yeah, word problems, okay? Or picture problems. Now, if I'm given something like this, and I'm told to find theta, what do I need?
One
Other
more.
side.
One other side. Which side would be the best? Best case scenario, which
Base.
side? You'd want the base, right?
Oh.
But here's the thing, right? In order, if the job is to find theta, if I'm told find theta, and I look at that and think, man, if I knew that base, I'd be home free, right? Because whatever that base is, I could say tan theta, which is our favorite one to take the inverse of, is 4 over b. And so therefore, theta is just arctan, 4 over b, and I don't have to worry about anything. Oh, what if b is 2? Oh no, then it's bigger than 1. Who cares? It's arctan. Arctan can handle it, right? So that's the idea. I mean, but maybe in the problem you're working on, this is the thing that you could find, whatever. But if you're given this, if this is the thing you're trying to find, you would need b, right? But what if your problem looked like this?
What?
Oops. Wait.
3-dimensional.
Well, yeah, you weren't supposed to know that. If you knew that that length was x,
Wait.
and that length was y. Now, if you're given actual values for x and y, would you be able to find what b is?
Yes.
Yeah.
How?
Because
Pythagorean.
it's Pythagorean here.
Cool. So everybody should get this problem, though.
Wait, what is the thing on the bottom?
Huh?
What's the thing on the bottom?
Well, you'll see. It's a poor drawing. The book has a good drawing. But this is my point, okay? You're going to have a setup like this. You're going to know what this is. You're going to know what that is. You're going to know what that is. You're not going to know what that is. It's going to tell you to find theta. And you could sit there and go all day, oh, I don't know what to do. Well, if you know that that's a 2 and that's a 4, then you could do some stuff to find what this is. And then it's super simple. So don't make it too hard on yourself, is all I'm saying.
So the hypotenuse of one triangle is the base of it.
Maybe. All right, just a couple more things to say, and then we're done. Okay, like I said, 64, 67, and 68 are from Chapter 6 review. And the answers are, for each one of these is in the back. The answers for every one of the chapter review ones is in the back, okay? Now here, on number 64, read it. Read number 64. There's a picture that goes along with it, but not all the information is in the picture. You're going to need to read it to find that missing bit of information that you need in order to solve the problem, okay? 67 and 68 are hard. They are hard questions. And I'm not going to go into how to do, you're going to have to figure that out. Like I could give you more hints and stuff like I just did with the other one. I don't want to, because I want to see how, like, you're going to have to work on these. In both cases, I'll go ahead and say this, you're going to want to construct right triangles. You're going to have somehow relate those things together. But I do want to say this. If you have two unknowns, how many equations do you need to solve them?
2.
Okay, so here we go. So if one equation looked like this, my two unknowns were, say, h and d, maybe I'm hinting at something.
Wait, this,
Maybe, I don't know. It could be hops and yeah, whatever. So if I had those two equations, can I solve for the two unknowns, h and d?
yeah, with a matrix.
Substitution.
Yeah, I could, but yeah,
Substitution.
Or
bunch of different ways. But one thing I noticed right off the bat.
together.
One thing I noticed right off the bat is that you have denominators. Let's get rid of the denominators first, okay? So in other words, this is the exact same thing as this, right? And so now, given these two equations, yes, you could use a matrix to figure this out. That would be no problem. Now it might be easier.
I can remember.
And here's another thing though.
But we just can set them equal.
Check that out. Is h equal to h?
Yeah.
Yes.
Always, right? H is always equal to h. And so, well, if h is equal to h, if that's equal to h, and if that's equal to h, then it must be the case that 5d is equal to 3d plus 50. Now what do I want to do?
Solve for D.
So
How do I do
minus
that?
the 3D.
Minus the 3d, leaving me what over here?
2D. So
2d is
equals
equal to
20.
what?
50, D is equal to 25.
d is equal to 25. Now, can I find h?
Yep, plug it in.
How would I do that? Into
Plug in
which one?
Simpler one.
The simpler ones. I guess, yeah, I mean, the answer's either one. You could do it in here, or you could do it right there. 5 times d is h, but since d is 25, then h equals what?
5.
5 times 25.
Which is?
Um,
How many, if you have 5 quarters?
125.
Buck 25. Right? That's how I did it. When I actually did this last night, I was like, I almost started like doing the multiplication. I was like, it's a buck 25, man. Okay, so, okay, right? Like, if I gave you this, you wouldn't have any problems. You just do this. Maybe you use a matrix and you'd be all right to do that. But this is what's going to mess you up.
oh.
This is what's going to mess you up is that if this is like sine 15 degrees, and if this is, say, tan 12 degrees, you're going to go, I don't know, do I need to take arctan? No! Once you plug in a value, this is just a number. Treat it like a number, right? Don't let this stuff mess you up. All the stuff that you've done up until this point in mathematics still applies. Okay? But this is why I'm bringing this up, because when you see this, you have something like this and you go, oh no. You forget that this is a number, right? And if you want, because ultimately I do think it says in 68 in particular, it says to use approximate values, keep 4 decimal places. Okay, so if you really wanted to, you could plug this in and find out what it is. It gives you 0 point whatever. And here's the thing though, if you choose to do it this way, since you're supposed to keep 4 decimal places, as you're doing the calculations, keep an extra decimal place in the calculations, okay? So then you've plugged this in and now you have this. It's much more similar to this type of thing, right? But I would suggest that you just wait until the very end of everything to actually evaluate this, because I guess it takes about the same amount of effort to write that and that. But again, now you've chopped this off, right? And if this shows up in some kind of crazy, I mean, it might be worse than this as you go on in your life and start doing this stuff, right? After you've chopped this off, because that's not the full picture. Sine 15 is not 0.12357. It actually goes on and on and on and on and on. And so why don't you wait until the very end to plug it in? That's what I suggest you do. If you have to do it the other way to see it as a number, okay? But remember, once you've actually plugged in a value into a trig function, then that now is a number. It's just a number. The same way that it was just 3. The same way that this was just 5. There's no difference. Yeah, so that's all I gotta say. Enjoy the homework and I'll see you Thursday.